All right, well, we'll go ahead and get going. So good afternoon, everybody, and welcome. My name is Chuck Raymond, and I am the Communications Manager here at Weston and Sampson. I want to say thank you very much for joining us for our latest webinar that we hope will be useful and informative for all of you. A few housekeeping items before I get to the speaker bios first, though. First, this webinar is being recorded, and we will make the recording available afterwards to all attendees. Secondly, all attendees are muted, and we are using the Q&A tool, not the chat, please, for any questions or comments you may have. And we'll be keeping track of them, and we'll get to them at the end of the webinar. And finally, contact information for each of our speakers will be available at the end of the presentation, in case there are, or at the beginning, in case there are any questions or anything else that you'd like to share outside the scope of this webinar. Now getting to speaker bios. First, Steve LaRosa is a senior technical leader and hydrogeologist at Weston Sampson. He has over 35 years of experience and is frequently invited to speak on PFAS-related topics like water and wastewater treatment, biosolids, landfill leachate, and others. Excuse me. He has designed and overseen the implementation of sampling and evaluation of PFAS contaminant sources and impacts at dozens of projects throughout the East Coast. He frequently interacts with state and regional officials and the EPA and citizen stakeholders to optimize project outcomes. Next, Matt McGuire is a senior project engineer in our Columbia, South Carolina office. His experience includes site assessment, solid waste, hazardous materials, and engineering design in a variety of facility demolition, decommissioning, and site redevelopment projects. For the past few years, most of his project work has supported clients that have landfills requiring post-closure monitoring services and helping them evaluate when sampling and analysis for PFAS may be needed. And last but certainly not least, Linda Cook is a senior technical leader and environmental chemist and data scientist. She has more than 35 years of experience specializing in the analysis, assessment, and interpretation of environmental chemistry data. For the past several years, most of her project work has supported clients to help them overcome the challenges associated with generating reliable PFAS chemistry data and help them interpret the data in support of project objectives and source identification. With that, you don't need to hear me talking anymore. We'll turn it over to Steve.
Great, thank you, Chuck. Just real quickly, I'd like to go over our agenda for today. We're going to do a very, very brief introduction into PFAS. We've assumed that you folks have signed on knowing what PFAS are and having a good sense of why these things are issues, but we'll just go over that very quickly. Then we'll look at what the current state of federal and state regulations are, take a look at the data that's been collected in the Carolinas, and then get into a little bit of information about the PFAS analytics and data reliability so that you can understand, how much veracity your data may or may not have. And then the best part, frankly, is the targeted case studies where we really kind of go over how PFAS can be evaluated and what maybe some of the tripping points are for a facility or an organization who has to deal with these. So what are PFAS? They are fully fluorinated compounds. They were man-made and have been used over the years since the 30s for a number of different things. Most people are familiar with Teflon coatings and waterproofing, aqueous film forming foams, AFFF, which is a fantastic firefighting foam used at a lot of airports. And then there's been all sorts of other things that PFAS have been utilized for. And in the last decade or two, folks have started to realize that there's some toxicity issues related with PFAS and that PFAS stick around for a long, long time. So where do we find this? What you'll find is that PFAS are in almost every man-made product that we encounter. Plastics, caulking, carpets, carpet cleaning, paints, even medical instruments like stents and other things that are used in the healthcare industry. Battery technology, there's lots of PFAS used there. So it's resulted in us having PFAS in essence everywhere throughout our environment, throughout our homes, and we all have PFAS in our bloodstreams, frankly, and there's very few places on Earth that they've sampled where PFAS aren't present. So, as I said, things are becoming concerning because of how ubiquitous PFAS are, and that we encounter them so much, and they are toxic at very low levels. And here's just a few snippets of some of the headlines associated with PFAS, where um, manufacturers, wastewater treatment plants, even stormwater treatment has resulted in PFAS contaminating water supplies. And even in Maine, they have some turkeys and deer that if you harvest them from a particular area, it's recommended you don't eat them because of how high the PFAS is. So all of this, again, comes back to risk and exposure. They're ubiquitous. They're called forever chemicals for a reason. Many of them do not break down at all in the human body or in the environment, and they bioaccumulate. So kind of like the old days with DDT. As you consume foods that have this, as you are exposed to carpets and dust, you're getting more and more of this PFAS in you. And it can cause, as you can see there, a myriad of potential issues from liver damage to cancer. And the concentrations by which you can see these impacts, particularly from drinking water, because we do drink so much water, can be from very, very low concentrations. As a matter of fact, the part per trillion level, which we'll talk about a little bit as we go along here. So let's jump to regulations. Let's jump to kind of, PFAS are everywhere. Well, what concentration or how much is a problem, and how's it being regulated? The EPA has really been focusing on regulating PFAS for almost a decade now. And they have a roadmap that they've generated, and it really comes down to the three tenets that are on the left. They want to restrict the use of PFAS and how it gets out into the environment. They want to remediate what's already out in the environment to again limit exposure, and then a lot of research to look into innovative ways to even test for these compounds, let alone clean up the environment and reduce our impacts. So drinking water is really where most of the regulatory work has been done, and where standards have been set for exposure to PFAS. Back in April of 2024, the EPA put forth a national primary drinking water regulation for 5 individual PFAS and a mixture of some other PFASs. And in May of this year, the EPA actually rescinded their recommendation for all but 2 individual PFAS. And those PFAS, they have very long names. Perfluorooctanoic acid is abbreviated as PFOA and PFOS. They're very similar molecules, but with sulfur containing one versus one that does not contain sulfur. These are the legacy PFAS that really have had the greatest use throughout history and seem to be the most prevalent in our environment. The goal for drinking water is actually set at 0. So not even a single molecule in the water that you drink. But unfortunately, we can't measure down that far. So the enforceable level for your public water supply has been set at 4 parts per trillion. And that testing needs to be going on right now at all of the public water supplies. And anyone who has a detection needs to let the public know, and they need to start designing and implementing solutions and treatments by the year 2031. The specific impact of this, I think, on the Carolinas really speaks to primarily North Carolina and the HFPODA, which is more ubiquitously known as Gen X. So that's the compound that in the Cape Fear area with Chemours is the biggest impact and problem. that's being seen out there in surface water and soils and drinking water, that compound is one of the ones that was removed from EPA's list. So that may have a significant impact on how that's regulated in the state. For South Carolina, I think a couple of the other compounds, the PFHXS and PFNA, are part of AFFF, but the PFOS is really the driver there. And so I don't think that removal of those other two compounds will impact whether a water supply is regulated in South Carolina by the EPA as much as the Gen X in North Carolina. So we're throwing out these numbers, parts per trillion and those things. To give you an idea, most contaminants that we see in drinking water are kind of regulated to the part per million or part per billion level. So that's 3 drops of this compound or chemical into a barrel of water as a part per million. When you start talking parts per trillion, we're talking about 10 drops in something like the Rose Bowl, a giant stadium worth of water. So we're really looking at, numbers of molecules in a glass of water to be at a part per trillion level. And that's extraordinarily hard to measure. And we'll touch on that a little bit later. So then the other thing that the EPA has done is what's called hazardous substance designation. Basically, this is the EPA's way of looking at all sorts of different chemicals and compounds and determining, are these prevalent enough and hazardous enough for us to want to regulate and to track their use and their releases. And PFOA and PFOS, again, those kind of heavy hitters, the ones that have been around the longest and used the most, rose to the top and were designated as hazardous substances back in 2024. Now, just like gasoline or dry cleaning solvent, there's a limit. You can have if you spill 3 drops, you don't need to report to the state. So it's 1 pound per 24 hours. And that actually is quite a bit of PFAS. If you spill that amount or release that amount, it needs to be reported. And the federal authorities are going to require that there's assessment and cleanup. The other thing that the hazardous substance designation has done is allowed the EPA to go back to all of their Superfund sites and sample them for PFAS because they weren't even tested for previously. So the EPA and the DOD and all the folks who are responsible for these Superfund sites are in the process of sampling them for PFAS. Right now, it's reported that there are 3 of the 66 Superfund sites in the Carolinas that have PFAS above the regulatory standards. So they aren't quite done sampling all of them or all of the units within the Superfund sites, but that's coming along. So it's worrisome that PFOA and PFAS are designated a hazardous substance because, as I started off with here, every single flush of the toilet, washing of your laundry, going to a car wash, all of these things release PFAS into the environment. So there was a lot of concern from wastewater treatment facilities, from your municipal sewage plants, that, hey, we receive this down the piping. We don't discharge this. What if there's a bunch of industry in our community and they're the ones who are discharging? Are we going to suddenly be made into a Superfund site or required to do cleanup? And EPA released a memorandum that talks about how are they going to try and enforce this new hazardous substance rule. And basically what they've said is, if you aren't handling or making PFAS-laden materials, then we aren't really all that interested in going to look at whether you have discharges. So that really made wastewater treatment plants and, like I said, some of the receivers of potentially contaminated materials that gave them quite a bit of cover for having liability. I will say, however, this is only a memorandum. It is not like the drinking water regulations where it's a law. So they could potentially change their mind as time goes by, but for right now, it seems like it's really only industrial style users that are really coming under the gun here. And then finally, for the federal regulations, they are setting water quality criteria for freshwater aquatic life. And this is a very complicated matrix of numbers and durations and exposures and these kinds of things. The thing to take away here is that we're talking about single digit part per million to single digit part per trillion allowable levels of PFAS in the water and in the fish that might be consumed, or say the deer, those kinds of things. So this is mainly just to show you that there are these kinds of regulations out there and recommendations. It gets really kind of into the weeds of assessment, but that is another federal regulation that is in place right now. So next, I think I'll hand it off to Matt, and he can talk about state-specific related regulations and how those are impacting folks.
Thanks, Steve. Yeah, so first we'll get into regulatory criteria and remediation criteria between North and South Carolina. As shown on the table, there are 8 separate medias for North and South Carolina that we were looking at. North Carolina currently has fish consumption advisories in place, interim and preliminary criteria for groundwater and soil, has proposed criteria for surface waters, but does not have any criteria for sediment, air, biosolids, and product in packaging at this time. South Carolina currently does not have any state regulatory criteria in place, but are conducting statewide surface water and tissue monitoring. In the next few slides, we'll go over North Carolina's interim maximum allowable concentrations, their IMAX, and preliminary soil remediation goals. So as shown on this slide, on the table on the right is the IMAC concentrations. The IMACs are developed for substances in groundwater that do not currently have an established standard and can be used to set up groundwater cleanup targets. Note that the PFOA and PFOS limits are 0.001 nanograms per liter and 0.7 nanograms per liter, respectively. These criteria are below most laboratory method detection limits. Per the EPA method 1633, the pooled MDLs for these compounds are 0.54 nanograms per liter and 0.63 nanograms per liter, which are fairly low. And next we'll go over to North Carolina's soil remediation goals. North Carolina preliminary soil remediation goals were developed using EPA regional screening levels. These values are to help advise and screen for remediation purposes and are not binding cleanup standards. Currently, there are 20 compounds that have listed PRSGs, but the most common PFAS are shown in the table on the right. To support ongoing evaluation of state regulations, North and South Carolina have conducted state-level testing, which we'll discuss next. So as mentioned previously, South Carolina has conducted statewide surface water and tissue monitoring. Ambient surface water monitoring was conducted over a 15-month period to investigate ambient concentrations of 26 different PFAS compounds in surface water, freshwater fish, blue crabs, and oysters. Based on the ambient surface water study, PFAS appear to be ubiquitous in surface water throughout South Carolina. Out of 205 stations, 149 stations had PFOS or PFOA at concentrations exceeding the EPA MCLs of 4 nanograms per liter. In 2024, South Carolina began a long-term monitoring study, which includes monitoring over 40 stations across 8 river basins. The LTM study is expected to continue for about 3 to 5 years. So under the Safe Drinking Water Act, It requires that once every 5 years, EPA issues a list of unregulated contaminants to be monitored by public water systems. The fifth unregulated contaminant monitoring rule, UCMR5, required monitoring at all community water systems, non-transient, non-community water systems serving 3,300 or more people, and a national representative sample of those serving fewer than 3,300 people for 29 PFAS compounds and lithium between 2023 and 2024, or 2025, excuse me. To date, about 6,500 public water systems have been tested, which includes 186 in North Carolina and 102 in South Carolina. Of these public water systems sampled in North Carolina and South Carolina, approximately 35% had MCL exceedances for PFOA and PFOS. To see how all of this is working in practice, we'll be discussing state-specific issues, including some ongoing litigation next. So South Carolina is home to the AFFF product liability MDL, which includes over 10,000 cases that span across state natural resource, individual property damage, public water system property, and personal injury claims. Currently, this MDL is still ongoing. Next slide. A lawsuit was also brought against DuPont and 3M and other companies for knowingly making and selling harmful chemicals to Galen Lord Textile Plant, a current Superfund site located in Society Hill, South Carolina. The lawsuit was requested to be dismissed, but was denied by a U.S. District Court judge. The Galen Lord Textile Mill was a mill and finishing facility that had on-site wastewater treatment operations. Upon closure in 2016, wastewater treatment operations were not properly closed. Additionally, approximately 10,000 acres of nearby farmland across 3 counties was contaminated from industrial sludge application. EPA is currently conducting a remedial investigation / feasibility study at the site and is monitoring local affected private drinking water supply wells impacted by the industrial sludge application. And now we'll talk about some North Carolina PFAS litigation. So in October 2020, North Carolina Attorney General Stein sued DuPont, Chemours, and other related companies, which include Old DuPont and Corteva, for contaminating air, land, water, and water throughout chemical manufacturing at Fayetteville Works. This lawsuit was won by the state of North Carolina. And AG Stein remarked, companies cannot engage in corporate shell games to avoid liability for the messes they make. I'm pleased that this ruling provides that Chemours, DuPont, and its related companies cannot avoid responsibility by engaging in corporate restructuring schemes. Our fight for clean water continues. Next slide. So North Carolina residents and homeowners along the Cape Fear River sued Chemours for dumping Gen X into the river, impacting drinking water and homes of more than 770,000 residents downstream of their Fayetteville Works facility. This lawsuit is still ongoing. The Department of Environmental Quality entered into a consent order with Chemours in February 2019. Fayetteville Works is an active manufacturing facility along the Cape Fear River. Next slide. The February 2019 consent order requires Chemours to address PFAS sources and contamination at the facility to prevent further impacts to air, soil, groundwater, and surface water. And this includes private well sampling, reducing PFAS discharges into the river, reducing air emissions of Gen X, conducting on and off-site comprehensive assessments of groundwater contamination, and other measures to characterize and reduce PFAS pollution leaving the site. Recently, Fayetteville Works requested Wilmington City Council to permit a facility expansion, which was ultimately denied by City Council due to fears that the expansion would result in further contamination. With that, I'll pass this over to Linda to discuss PFAS analysis and data quality.
Hi, thanks, Matt. So I could really spend an entire hour, maybe even an entire day, getting into the details of PFAS testing. but I'm going to save that for another date. Today, I'm only going to be highlighting some details related to PFAS testing. But of course, if you had any detailed questions you'd like to ask, please feel free to reach out. So there's really only a small subset of PFAS compounds that can be tested for using the published EPA methods. And depending on which method you choose or the laboratory, that list of targeted PFAS varies from, maybe 20 to 100 different compounds. But literally, there are tens of thousands of PFAS compounds. So we're only capturing just a few with our targeted testing. Published methods for samples other than drinking water were really slow to be finalized. So in the meantime, laboratories themselves created modified methods to test for PFAS in other matrices, soils, consumer products. And in some cases, they expanded those compound lists to, as I say, capture up to like 100 different compounds in some cases. But that's really the extent of the targeted PFAS testing. The most common methods we have right now, there's many published methods, but the most common ones are method 533 and 537, which are applicable to drinking water samples. And then recently, method 1633 was finalized for basically all of their matrices other than drinking water. So in method 1633, it stated that it was applicable to Clean Water Act testing, but yet it has not yet been promulgated under 40 CFR Part 136, which does list those approved methods. However, we know that 1633 is starting to be used more frequently, and really we're just waiting for that approval under 40 CFR Part 136. We're expecting it soon. We just don't know when at this point. Just want to state that these targeted PFAS methods, they're really technically very difficult. There's unique instrumentation, there's lots of method complexities, and the ubiquitous nature of PFAS in the laboratory environment makes it difficult for laboratories. You really need a PFAS clean room with no products that contain PFAS. As Steve said, PFAS are everywhere, so that's difficult. I mean, lab technicians even need to be careful with the cosmetics they use, their laundry detergent, and what they're wearing. For these methods, detection limits are really low. They're in the part per trillion range for water samples and the part per billion range for solid samples. But we're only detecting 100 compounds. If we want to know more about what's in our sample, those tens of thousands of compounds, how do we go about detecting for some of those PFAS? So there's compounds that are referred to as PFAS precursors. And precursors are chemicals that are PFAS, but they're not included in that short list of targeted PFAS. And these precursors can degrade into the environment into what we call terminal products. And a terminal product is just a compound that can't degrade any further. And so Steve talked about these being forever chemicals, and indeed they are. But some of these compounds can degrade to more simpler PFAS, but the PFAS themselves, those carbon-fluorine bonds are so strong that really those shorter chain carbons with, fluorine really do not degrade after that. It's more of these bigger, more complex molecules. So the figure on the right is a great example of what this complex network would look like with PFAS compounds. So in this case, we have PFOA as the central hub in this network. And all of the compounds, the individual compounds surrounding that PFOA are precursors. And based on degradation, they can degrade, forming degradation products and ultimately forming that PFOA compound, which would be a terminal product that would not degrade any further than that. And PFOA we can detect with our testing. So this is just a schematic for PFOA. We could develop similar schematics for all of the carboxylic acids of varying chain lengths. And this just gives you an indication of really how complex that world of PFAS really is. So now how do we go about detecting for these precursors? So researchers and labs have developed a method that's referred to as total oxidizable precursor analysis. There is not yet a standard method for this, but there are standard approaches that laboratories are using. The sample is treated with a strong oxidant to degrade all those complex PFAS in the simpler terminal products that we can then detect with our targeted PFAS methods. There are a lot of technical challenges associated with this method. Again, I'd be happy to discuss with you offline. We just don't have the time today to go into those details. The figure on the right illustrates with highlighting those PFAS classes that can be measured using this method. So we definitely get more PFAS mass with this method, but we don't get it all. You know, we miss the fluoropolymers, which are just so robust that they don't break down into short chain detectable PFAS, for example. Top analysis is used as a proxy for total PFAS in a sample. However, as you can see, you know, we're not capturing all classes, so it's really a low estimate of total PFAS. And as I mentioned, no currently approved methods, but EPA and other organizations are working to develop standardized methods. And as with our targeted testing, the detection limits are the same for our top analysis, with detection limits in the part per trillion and part per billion range. So along with method 1633, when that was published as a final method, they also published method 1621, which is for adsorbable organic fluorine. And this is for aqueous samples. And again, this provides a proxy for total PFAS. And in this method, it also notes that it can be used for monitoring under the Clean Water Act. But again, it's not yet promulgated as that 40 CFR Part 136 method. So now, based on the figure on the right with the highlighting, you can see this method, again, does not capture all of the organic fluorine in the sample, but it does capture more than the top analysis. We are seeing the AOF method is starting to be required in NIPSD's permits as a monitoring requirement. There are no limits at this time, but we do expect limits will be developed in the future for wastewater treatment. And by using this adsorbable organic fluorine method, they'll be capturing what a total PFAS load is, not just the targeted PFAS included in those standard methods. So here's a real world example of the difference in total organic fluorine in a sample versus what we'd measure with targeted PFAS. So in this study, they used a different method. It was extractable organic fluorine as a measure of total organic fluorine. So in this case, when they summed all of the detected PFAS in these samples, it was only about 2% of the mass of the total organic fluorine in this sample. So this large difference is likely because the organic fluorine measurement it will capture some short chain PFAS, which we haven't talked about today, but those are PFAS containing less than 4 carbons. And it will also capture some of those PFAS precursors we talked about and some additional fluoropolymers which aren't captured by targeted methods. So as I mentioned before, PFAS is not a routine analytical method. It's really difficult and challenging. I started my consulting career back when dioxin analyses were, the trendy topic. And that method was really considered specialty. It was normally only performed by specialty laboratories. Really, I only remember a handful of laboratories that did it well and routinely. What I can tell you is PFAS testing is even more difficult and more challenging. However, we're seeing so many laboratories jumping into this market because there's huge growth potential for the lab. However, these labs, they're not specialty laboratories. They're used to routine analytical work, and they just don't have the experience and expertise to perform this method reliably. And some of those data use challenges when we're looking at data across multiple laboratories, that we're seeing large differences in detection limits variability in the results and the quality of those results, a lack of consistency when we've transitioned one project from one lab to another lab, and we start seeing differences in what's being detected in those relative concentrations. False positives are common because of organic interferences, especially when we're looking at wastewater samples. False negatives are occurring, but those are much more difficult to detect because, we're not seeing them on our data report. And when you have less reliability in your data, it really can degrade the trust both with your regulators and your customers. So, we're making multi-million-dollar decisions based off PFAS testing data. And if these data aren't reliable, then that foundation of your financial decision's not solid. Getting good quality PFAS data from the start really takes proactive planning and effort, and it's likely to increase some program costs. But those proactive data quality tasks, you can plan them and schedule them and budget for them. They're included in your plan. Whereas costs associated with the impact of dealing with poor quality data, and what I'm talking about in the slide here as those reactive costs, they can't be planned or scheduled or budgeted. So when you get poor quality data, you might have to rework, resample. It causes schedule delays. You might not get the data that you need or the data that you want. Can increase design costs, or maybe your design won't be as robust as it needs to be. And in the world of PFAS, we're seeing a lot of litigation. You want your data to be able to withstand the scrutiny of litigation. If you have poor quality data, that will be ineffective in your litigation support. So with proper proactive QA planning and oversight, your team should be able to generate data that are suitable for your current project needs, but really able to support those high value decisions and can be repurposed to support future needs such as litigation if that's ever required. So the question I always ask is, do your data make sense? And so here's one case that I was, a colleague provided me with these data. It was from a treatment system. We had influent results, mid-fluent results, and effluent results. The influent looked as we expected. It had PFAS contamination. That's why we were treating the water. Our mid-fluent was non-detect for all compounds. That's as we expected. But then in our effluent sample, we got a hit of 50 nanograms per liter of 6,2 FTS. That was not expected. It did not make sense. We went back and questioned the laboratory. We pushed the laboratory to re-extract and reanalyze our sample. And that re-extraction and analysis showed that 6,2 FTS was not present in that sample. In this case, that detection was a result of a laboratory contaminant. In this case, we actually were dealing with field contamination. So this was a case where a water sample was being collected from a private home. We were unable to access the well at its point of entry into the house. So we were collecting samples from a spigot outside the house. There was a hose attached that was removed. The spigot was wiped. The primary sample was collected, and then the field duplicate. And thankfully, we had that duplicate sample because when the data came back, we saw a really high detection of PFNA, 67 nanograms per liter. This is a regulated compound in the state of Mass, so this was problematic. This was a private resident. We were going to have to report these data to the individual who lived in this house, and that would have been very concerning for them. There's an emotional cost to poor quality data. Fortunately, we were able to really quickly go out, resample to confirm, and we were able to confirm that that house had no detected PFAS. What we believed happened is a small particle of that gasket may have ended up in this sample. And, so small we might not have even seen it because, again, we're dealing with levels of parts per trillion. Another data reliability challenge we have, and it's not really that the data aren't reliable, but when we're starting to investigate our sites, There's many non-point sources that contribute to regional PFAS background levels. These are really difficult to regulate. They may be coming from domestic septic systems, hard to really find and pinpoint because they're so diffuse, and really mitigating them because it's not a point source. We can remediate our point source, but when our whole regional background has impacts, that's very difficult. So for site investigations, the impact of these non-point sources are important. We really need to understand them so that we can refine the remediation strategies as well as incorporate that background into our risk assessment. And just as an example, here's data for a site we're working on. This is the upgradient monitoring well that's associated with our site. And at this site, it's not really background, it's more this anthropogenic background. We have exceedances of both the PFOS and PFOA MCL of 4 nanograms per liter often. And with this regional background coming onto our site, it really makes it impossible for us to remediate sites to levels that are less than the MCLs. But I'm going to jump into my case studies now. We can talk about this particular one a little bit more. So the first case study I want to talk about is the use of forensics in site investigations. So we have a site, we have a source property, we know we have a PFAS point source here. We know that PFAS products were used in the past. When we looked at the contamination in the groundwater, and we were focusing just on a summed parameter of 6 of the PFAS, it really looked like not only had we impacted our site, but properties next to us, as well as down gradient monitoring wells and drinking water wells, which were even further down gradient. So we wanted to look at the forensic. Is our signature different than other signatures in the area? And what we see in the histogram to the top right is our source. And our source was dominant in PFOS. So that is that blue bar all the way to the right is our PFOS. That was our source based on historic records. We're confident that that's what we're impacting the site with. But then we looked at background, that upgradient well that I had shown you. And the source there was quite different. It actually had a different profile. It had the compound PFOA at a relatively higher concentration than PFOS. And so here you can see that to be the largest peak, somewhat in the center of that background histogram on the lower right. And we did a lot of evaluation of the data, and we really came up with 2 parameters that we could monitor in our system, in our wells that surrounded our site. Just simply that absolute PFOS concentration, and then the relative ratio of PFOS to PFOA. So we also had a stream that started upgrading from our site and kind of, circled our site. And that was a losing stream that was not being impacted by groundwater. And we found the stream profile to also be similar to our backgrounds. We looked at the properties adjacent to our site, the bottom left and right graphs. And again, we saw that predominance of the carboxylic acids in a high relative concentration of PFOA, and saw that that was indeed different from what we had at our site, which was PFOS dominant. So using all of this data, and there are additional analyses that were done, really the bottom line here is that performing this forensic analysis, we were able to reduce the footprint and the size of the groundwater plume that we had impacted. So we were able to reduce our impacts. And so now we weren't impacting the adjacent properties. There was impact at some down gradient wells, and really very minor impact at the drinking water wells, even further downstream from down gradient from us. The next case study I want to talk about really involves investigating your supply chain. So potential sources of PFAS can be introduced into, say, a wastewater stream at your facility from any product that you use in the process, including cleaning products that you might be using on site. In many cases, suppliers of these products, they're not even aware that their product contains PFAS. Unless they've intentionally added it, there can be unintentional contamination in their products. And, we know that our supply chains are complex. They're very global in nature. They're many tiers deep. And the products that we're using in our manufacturing, they can change over time, and we might not even be informed. And PFAS ingredients, often, if you're looking at that SDS, PFAS ingredients may not even be listed as they're considered proprietary ingredients. So even the SDSs often do not supply you with the information to know, does this product I'm using contain PFAS? As I said, they can be unintentionally introduced into your process from sources if you're using any recycled products. Even contaminated local groundwater that you're using can impact your discharge, especially if there's any concentration of that during your process. If there's any concentration of that water stream, again, that would increase those PFAS concentrations. And while these types of indirect or unintentional PFAS sources, they're likely to introduce low concentrations. These low concentrations can still be detected. They're still of concern to regulators and neighbors. And when we're talking about PFOS and PFOA, we're talking about really small, 4 nanograms per liter is a tiny amount. So in this case, our mission was to remove PFAS from a textile manufacturing process so that we could remove it from the wastewater. And, the first pass at this process was to evaluate every product that was being used and remove those that were known PFAS sources, and then detect the wastewater, test the wastewater. And we were really confident that we were going to see a decrease in concentration, but we didn't. Those PFAS were still in the wastewater. So then we tested every suspect product, just using a traditional PFAS target analysis for those, I think it was about 40 compounds. And we found some sources and we removed them, and they were still finding PFAS in the wastewater. It's so frustrating. They cleaned their wastewater streams in case there was any residual wastewater, PFAS clinging to the system, and we were still detecting it. So finally, it was really an expensive, long process, but every material that they used in that facility was tested by top analysis to find, are there PFAS precursors? And we did. We found evidence of unintentional PFAS precursors in supply chain materials. One ingredient that we tested had a really high PFAS concentration. It's broadly used in household cleaning products. And that was one of the primary sources to this wastewater stream. So I just want to say what I learned from this is vendors will give you PFAS disclosure statements saying no PFAS, and they may be correct in saying no intentionally added PFAS, but do not trust those blindly. You really, if you're finding PFAS in your wastewater stream, kind of need to go upstream of your process and start testing your products. I'm going to pass the baton to Steve now. He's going to talk about some treatment solutions.
Great. Thank you, Linda.
Steve, I'm sorry, just a quick heads up. We've got 11 minutes left. Thank you.
Gotcha. So how do we pull these compounds out of our environment? How do we get them so that we don't become exposed to them? And really the methodology, again, has really focused on drinking water. It's where we have the potential to have the highest exposure a lot of the times. And there's basically 3 commercialized methodologies. There's granular activated carbon, which absorbs the PFAS out of the water. Basically, the PFAS will stick to the carbon, and you'll have clean water coming out. Ion exchange resin, which is a very specialized formulated bead, basically, that does the same kind of thing as granular activated carbon. It will The PFAS will stick to that as opposed to being in the water. And these are two technologies that have been used for decades and are being implemented quite a bit throughout the Carolinas. A lot of the Cape Fear related waters are being filtered at each of the public water systems using granular activated carbon. Ion exchange resin is a little bit more sensitive to some of the water quality and conditions that you have in the surface waters that you're using for drinking water. So it hasn't been used quite as much. The third method is reverse osmosis. And what this is it's basically a membrane technology. So think of it as a very, very tiny, almost molecular sieve, so that things that aren't an H2O molecule stay in the membrane, and the H2O water goes to the outside of the membrane, so that you have basically pure water is all that comes through these. You also have a couple of huge reverse osmosis plants that are operating in both Carolinas as a result of just wanting to have the best filtration possible, or because of PFAS presence. The benefit of reverse osmosis is that it also will filter out lots of other contaminants that maybe won't stick to granular activated carbon or ion exchange resin. Lots of pharmaceuticals, bacteria and alga will be kept out by reverse osmosis. So that is a very viable treatment methodology that a lot of folks down there are using. Let's talk about limitations with that. Each one of those filtration methods has a waste product, either expended carbon and resin, or when you filter all the water, you've still got this brine of what wasn't water that went through the RO, and that has to be discharged somewhere. And as we talked earlier, if the concentrations are such that you're above the CERCLA limit, you may be limited as to where you can bring that. And frankly, there are a lot of landfills and incinerators out there that won't take the carbon or resin and incinerate the PFAS there. Other limitations are, again, if you've got a complex water quality, carbon and resin may not work very well. And then you will, after a lot of these filtration systems, need to disinfect. And as you can tell from all of these, they're expensive. They're expensive to run, they're expensive to maintain, and they're expensive to install. So, our concluding thoughts. We've thrown a lot at you today about PFAS and about what's happening in your states and what the regulations are. And kind of the sound bites that we'd like you to leave with are PFAS are nearly everywhere. They're quote background or anthropogenic background. So you're going to run into them, be it soils at a development site, or your drinking water, or discharge from your wastewater treatment plants. There's a really good chance these are around. They're very difficult to test for, and you really need to look hard at what your results are. Do they make sense? Do we have a regulatory related issue or not? The regulations are changing. They're changing frequently. And for the most part, states and the federal government are putting the numbers that are acceptable lower and lower. Treatment and destruction is complicated and expensive. And at the end of the day, the potential liability for either using or disposing of PFAS, PFAS treatment, and PFAS in residuals like sludge or wastewater, that potential liability can be very high. It costs a lot of money to clean up and assess these impacts. And even if you're following today's rules, you may end up having liability in the long run due to your methods of disposal or how you're going through your process. So that's really it for us. As I said, it's an awful lot. We're more than happy to talk to you about any details you might want to talk about or to clarify any questions you might have. We've got, I think, 5 minutes here, and then our contact information is contained here. And as Chuck said, we'll get our whole slide deck here off to you after we're all done, along with our recording.
All right. Thank you, Steve. Thank you, Linda, and thank you, Matthew. That was great information. Really appreciate it. So seeing as how there aren't any questions that I'm seeing in the Q&A, we'll go ahead and sign off and let you get on with the rest of your day. Just to sum up, as mentioned earlier, the webinar was recorded, and we'll make the recording available to all the attendees. And note, we will also be sending attendees a CEU form that you can submit as you see fit to your individual certifying agency. And just note that though that our CEUs are not pre-approved by any particular organization or state regulatory agency and may not be applicable for all certification programs, but you are certainly welcome to submit it and see what happens. Lastly, please feel free to reach out directly to any of our presenters. Their contact information is here with any questions that you'd like to share outside the scope of the webinar. And with that, thank you very much for attending and have a wonderful rest of your week. Take care. Bye-bye.
Bye-bye.
Thank you all.